Next, we will look at set operations, and again, these are quite well known. First of all, let's define the concept of a universal set. The set that contains all elements in a context is called the universal set. If you match this to the concepts in logic, this corresponds to the domain of discourse. Okay, so whatever elements that are meaningful in the context, they are all elements in the universal set. And we have the two most elementary set operations, union and intersection, defined as in here. A union B is a set again, defined as the set of all x's where x is an element of A or x is an element in B. So the cumulative collection of the elements from both A and B. This gives you the set union. What about intersection? The set of intersection of A and B is simply the set of x's such that x is in A and x is in B. So the list of, or the set of elements that are both in A and B, okay, the common elements. Now the set difference, you have A difference B. Uh, this is the set of all x's that are in A and not in B. Okay, so the set of elements in A that are not in B. And of course, in some text, you can see the notation as this here. And you can also show that this is equal to the set A intersection with B complement. So what is a complement? Let's define the complement of a set. A complement, we will use this notation usually, but sometimes you can see this A to a superscript C. This is the set of x's where x is not in A. Or simply, this is the set difference between the universal set and set A. Okay, so simply, let's say you have this universal set here. Let me use the traditional explanation. Let's say this is set A, this is set B. Of course, the union is both of these, A union B, and the intersection is here, A intersection B, and set difference, this is A difference B, and let me also indicate B difference A. And we also have this concept of symmetric difference. This is the notation. Well, there are also other notations. Sometimes you can see this with a triangle. There are also some others that are very less used. But essentially, this is the set of x's that are either in B, in A, or in B, but not both. So the definition involves an XOR function here. Essentially, this is the union of A difference B and B difference A. Or you can just obtain this by the set difference from the union of A and B and the intersection of A and B. If you have two sets A and B, this here together with this constitutes the symmetric difference. Now, of course, based on these definitions, we have a number of identities, and these can usually be proven using logical relationships, which I'm not going to do. Most of them are not that easy. It's not that difficult. You can just plug in the definition. For instance, here you can just plug in the definition of union and then obtain the truth of this expression as a logical proposition. The only manipulations you will need probably are related to propositional relations, and that mean for that reason I'm not going to do one by one each of these, but essentially that's how you prove these. So we have the identity laws. A union empty set is equal to A itself, and for each of these identities except for this one, we have what we call a dual. So here we have usually based on definitions based on union, and on the right hand side we have the identities based on intersection. And when we say the dual expression, we mean you switch unions to intersections and vice versa, and you also switch um, empty sets into universal sets and vice versa. So when you make this an intersection and this a universal set, okay, so you obtain this, and they are dual expressions of each other, and they have the same truth value. And we have the domination laws here. Of course, here I should have the universal set forgotten here. A union with universal set is equal to universal set, and A intersection with the empty set is equal to the empty set. We have idempotent laws. The intersection and union of a set with itself is equal to itself. We have commutative laws, okay? Union and intersection, they both commute. So it doesn't matter which order you put in the operands of the union or intersection. We have associative laws. The placement of the parentheses here doesn't matter. We have distributive laws. Here, bear in mind, both of them distribute over the other. So here, union distributes over intersection, and on the right-hand side, intersection distributes over union also. Okay, so this is a little bit different than distribution in just arithmetic. So for instance, if you remember, we have like x times y plus z. We can write this as xy plus xz, but if you have x plus yz, you cannot write this as x plus y times x plus z. But here you see we have distribution both ways. Union distributes over intersection, but also intersection distributes on over union. And we have De Morgan's laws, almost exactly the same with what we had in propositional logic. And in fact, you can prove these using those De Morgan's laws in propositional logic. If you have the complement of intersection, it's equal to the union of complements, and similarly, complement of union is equal to intersection of complements. And we have the absorption laws. A union with A intersection B is A itself, and A intersection with A union B is equal to A itself. Um, and we have the complement laws. If you take the union of A with its complement, you get the universal set. If you take the intersection, you get the empty set. And finally, we have the double complement law, where you complement a set twice, you obtain the same set.